And in the this is the negative current. In the first half cycle, no red. So up to this point here, this node is more positive than this node, which I'll do in blue. So I'm going to assume that since the capacitor can't charge quickly, it can't charge quickly at the moment because the diode's off and the resistor's large. So there is no significant amount of charge able to pass into this capacitor because this resistor stops it in the period of time that we're interested in. So this node becomes high voltage as well. If this capacitor can't charge up, then it can't have any voltage across it. If it hasn't got any voltage across it, whatever we've got over here must appear over here. As it charges up, a voltage difference will appear due to I dV by dt, or V is 1 over C integral I dt, or whichever you prefer. So all this stuff's blue, and we get a small current. Currents will be in yellow. A small current goes up there, down there, and down there, and makes this plate more positive than this plate, ever so slightly, but hardly anything at all. Basically still 0 volts across the capacitor. As a consequence, the output voltage, which will measure across RL and will be in blue, just does that. And this situation carries on until we get to minus 0.7 volts, which is the turn-on voltage of the diode. So by the time we get to that 0.7 volts, the situation has changed, ball rubber. Got rubber and everything. The situation's changed so that this is now the more positive node, and this node is more negative. Capacitor's still not charged, but now the diode is, and there is no significant charging of the capacitor at the instant the diode turns on. So 0.7 volts across the diode, in the right direction, still no current flowing. So we've still got nothing across this, no voltage across the capacitor because there still hasn't been any charge put into it. But luckily we have 0.7 volts across there now. So this diode's about to conduct. And if you could press play on the diagram, next thing that happens is this voltage gets a bit smaller compared to this one. So this gets a bit bigger and a current flows out of here through the diode and onto this plate of this capacitor. And this current is large. It will easily fill that capacitor quickly, certainly in the time that's available before anything interesting happens thereafter. The resistor still isn't up to much, but there is a little current that flows through it which assists this charging, but it's negligible in comparison to the current that flows through the diode. So we have large current flows through the diode, and the output voltage, which we're measuring across the resistor, notice the direction of the arrow is opposite. It can't actually fall as low or as high as the source would have it because the diode is in parallel with the resistor and it clamps it, hence the name, at minus 0.7 is the case of we call this positive output, and we call this negative output. If you prefer to say that this is the output that I think is important and this is my reference, then it'll be 0.7, and that graph should just be flipped. It's entirely up to you, but usually we would call this negative clamp because we like to think about the references being at the bottom of the diagram. Right, who's got the graphs? Because I don't want to draw it wrong. Or should I just go and download them? Go and have a quick look, see what I wrote. Just in case you really can't find my lecture notes, this is where they live. These, yeah, that's not my, oh, don't do that, electrons and holes, terrible. So this is last year's, but they are broadly speaking the same, because I'm lazy. It's not that I can't remember this graph, it's just that I can't remember this graph. But can't remember it isn't the same as doesn't know what's going on. So the current ceases in line with, sorry that should be white, in line with the bottom of this waveform. So when this waveform reaches a minima, if we took the gradient here, we'd say no change. And if we took the gradient here, we'd say going up, the voltage is increasing. This means that the situation on the diode is now that it won't be forward biased anymore. It will actually fall away from 0.7 and the diode will switch off. And when it does that, the current ceases. Strictly speaking, what happens is the current ceases and therefore the diode turns off. It's not a case of take away the voltage and the diode stops conducting. It's take away the current and the voltage will go away. And all at the same time, we say the diode stops conducting. That's important later because a lot of rectifying applications, which we'll discuss shortly, deal with electrical machines. And in the case of electrical machines, you have an inductance usually, which is part of the machine, and the inductor wants to keep the current flowing, and it will put some voltage up to try and make that happen. And when we drive electrical machines with bridges of diodes, which we'll see, we won't see it with machines now, but you will at some point, especially in 307 or whatever it's been replaced with, there will be the case where you think the diode's going to switch off now because the voltage has disappeared, but the current keeps going and that makes the voltage stay. And you'll look at it and go, oh, that's very strange. So the question of when the diode is off is when the current stops. But the current will stop because the voltage is changing direction. So that will cause the diode to switch off. And the situation at the point of switching off will be that this plate is considerably more positive in voltage than that. Yeah. Considerably more positive in voltage than that way. So we just finished this bit here, that third quarter cycle, and this voltage is rising. Now, diode switched off, resistor's still big, and this region here has now got the bigger voltage. And this capacitor can't charge, because the only way it can charge up is by having a current through the resistor. And the resistor is very large, so not going to be enough current, no appreciable change in charge, no appreciable integrated charge, no appreciable change in voltage. So if this voltage is rising, and this one's already bigger than this one, the only thing that can happen is they both go up together. Which is what happened in the, well, I might as well just do it up here, look. We are between 0.75 and 1.25 milliseconds. Both of the input voltage and the output voltage, which is black, input's blue, both go up together. And that's just the case of there is no net charge really flowing in the circuit. Very small amount through the resistor, but basically none. And that is the action of the clamp. So you could say that the clamping bit happens in the third quarter cycle, where the diode is conducting and charging up the capacitor. Have a go at the problem sheets and you'll feel much better about it. The other thing to know, of course, is it's almost the same sort of thing that happens in the peak detector, in the sense that you've got a period in time where a waveform exists that causes the diode to be switched on, and that causes the capacitor to charge up, and then later the diode switches off and the resistor discharges the capacitor. It's the same set of events, actually in more or less the same order. The only thing that's changed is the arrangement of diode and capacitor mean that the waveforms look different. It's not conceptually any more troubling, although it usually does produce a lot of difficulty. Right, enough of that. Today's lecture. So this is what we did last time, which I just talked about a bit. And today I'm going to do power supplies of the linear kind. I'm going to talk about three-phase for a bit. And then we'll talk properly about rectifier circuits, which you'll be pleased to know are secretly just peak detector circuits with a new name. Is he alright over there? Oh, you are, you're alive. Good man. I'm going to keep my kill ratio down. So we're going to spend most of this lecture talking about rectifier circuits. So rectification, if you needed a definition, maybe for a mark or two, is the conversion of an AC voltage into a unipolar voltage that is usually in the form of DC component with superimposed AC component. So this goes back to my DC is not constant. All you need is an average which is bigger than 0 or lower than 0, and you can have any amount of ripple on top. So DC component is the average value. So if I was to integrate across a period, so you do 1 upon t integral v dt, where you do from integration from 0 to 1 period, you'll end up with some number, and that's the DC bit. Assuming it's not 0, if it is, there isn't any DC. And all the stuff that's on top of that, all the ripple, is the AC bits. And the rectifier circuits generally are divided into half wave and full wave. And the half wave is more simple, so we'll start with that one. No, we won't. We'll talk about three-phase first. So, in a domestic situation, there is one line, one neutral and one earth in Britain in a three-wire system. And discounting the earth for a bit, there is one voltage which is half the time bigger than the neutral, then the same line carries a voltage which is the other half the time less than the neutral. In situations where we want to supply a lot of power, usually we'll take three lines in which are carrying a voltage which varies with respect to the neutral, and the time relationship between those voltages is shown in the graph on the slide. The advantage of this is we can provide more power, and that we can recharge any energy storage components, capacitors or inductors, 3 times more frequently. The result of this is, well, if you were to get a motor and make some construction whereby you stop the rotor from turning, so the rotor is the turning bit in the middle. If you just grab it, the motor will try, and we'll assume the simplest situation where it's a DC motor supplied by some simple circuit. You'll find that there's only torque when there's current, and there'll only be current when your rectifier is conducting, because you've got your hand on the, well, you've got some mechanism of holding them. I wouldn't put your hand on it, it wouldn't do any good, but you've got some mechanism of stalling the machine. The torque will come in pulses, and those pulses will make the machine vibrate. Not only will they make the machine in front of you vibrate, the transformer in the substation that's supplying wherever you are with electricity to run that machine will also have those mechanical vibrations induced in it. Much smaller, because that transformer will be a lot larger. But in the case of very heavy industry, you have to worry about the bolts on your transformers that keep them on the concrete slabs from getting loose over time, because the transformers vibrate a bit. And having three-phase not only allows more power, it allows us to minimise the mechanical vibrations that are set up. And we can also use some circuit tricks to minimise them as well. Principally, we want to even out the current flow. But the dominant reason for three-phase is we just need more power. So presently it's brown, grey, black and black. 3, that's right. Previously it was red, yellow and blue. So if I say red or yellow or blue, what I really mean is brown or black and grey. So the single phase in the UK that comes in to a domestic situation is 240 volt RMS at 50 Hz, which means peak, the sine wave will be root 2 times, which is 339. If you look at our standards, it says 230, but actually it's 240. If you measure it carefully, you just get a plug. I'll edit this out. Get a plug, take the back off, plug it in, switch it on, get a meter, and just put it across the live and the neutral on AC. Make sure you know what you're doing first. You'll get a measure of the mains at the point where you're taking it off. And it varies quite a lot actually. It will vary. One thing you can do is do it downstairs, run upstairs, turn your power shower on, run back down and have a look. Be careful. Anyway, so we say it's 230, but actually we supply 240, and we said that 230 to comply with the rest of Europe. But we've stuck with 240. Any thoughts on why? Belligerent British? Not that. It's an economic reason. If a power company supplies you with 240, and you've got some light bulb which is notionally 60 watts, it will draw a certain current and you'll get I2R power loss in the bulb. If you supply with 230, or even better, you'll get V squared upon R, makes it more obvious. If you're supplied with 230, your V squared's dropped by 10 squared, which is actually quite a lot. It turns out that it's about 8% less power supply, and they can't charge you for any power they don't supply, although I'm sure they'd like to. So what we're really saying is if we lower the voltage a bit, you get charged less, which means they get less money, and they really like money, a lot. So that may be a little bit cynical, but I'm certain there is a certain amount of truth behind it. So that's broadly what comes out of the mains. The specification for frequency is plus minus half a hertz. The reason it's quite a tight spec is some clocks run off it, but that's neither here nor there. If you lower the frequency too much, and you've got some electrical machine, and you've designed your machine quite carefully, the flux that's in your machine will be proportional. Well, you've designed it carefully, and the flux is proportional to the current that's flowing in the turns, which induces the B field in the magnetic components. If you lower the frequency, your B field goes up and you saturate your transformer machine, whatever it is. And that's tricky because when you saturate your magnetic material, large currents tend to flow. And that's obviously they have to supply those large currents. So let's talk about some rectifier circuits for a bit. I'm not really worried about what happens inside the transformer. You can think of it as a black box where you put one voltage in with some current and you get another voltage out with some current, and the current times the voltage adds up to the current times the voltage. That's fine. I'm not going to bother with how you construct a transformer or what the flux should be or turn ratio or any of that stuff. It's just volts and amps. And what we've got thereafter is a peak detector minus the capacitor. So we're down to just 2 components now. And the graph is below. And essentially when the voltage on the secondary, which is A to B, where A is bigger, is more than 0.7, the diode will conduct, and it will conduct a current through the resistor back into the other terminal of the transformer, secondary. And that current will be proportional to the size of the resistance, so obviously the current and voltage look the same, because V is IR. The lower half cycle, the second half cycle, and the fourth half cycle, and so on, don't get a look in. So the current actually only flows for half the time. So if you were driving a machine off this and it was DC, you'd get torque, no torque, torque, no torque, and so on. So it's actually it's rhythmic, which is what sets up the oscillations, and you don't actually extract very much power. Now we can add something to this to try and smooth out the current. Now, hang on, I've got to say some other things first. So, yes, the wave shape is unacceptable, which is broadly what I've just said. And realistically, we'd like DC all the time because there is a period between 10 and 20 milliseconds and also between 30 and 40 milliseconds where there is no output voltage at all. So if you could see without the persistence of vision and you had a light bulb on it, you'd see it going on and off. But we don't see that because vision has long persistence compared to the time involved. If you had some photo detector or some such and you connected up to an oscilloscope, you'd be able to see a line on the oscilloscope screen which is proportional to the light coming out of the bulb. So there is an average value and it is positive. So we've got DC even though it spends half its time at zero. And we're saying obviously the AC component is very large. So what we'd really like is to smooth out the current flow and to get a voltage which is always more than zero. Now, it's never less than zero, but it spends half its time at zero, which isn't really very useful. So what we really want is to fill in the gaps. And we can fill in the gaps with a capacitor. So this is a peak detector driven by a voltage source, essentially. The transformer is only there as a sort of extra to make it into a power supply. So this is the same sort of graph that we saw on, whenever it was we saw it. Was it Monday last week? Whenever. And I've got the situation where the black line is just about triangular. So we're on the point where we're breaking our rule of we'd quite like to keep the discharge of the capacitor not looking like an exponential straight line. And we can see that the current now flows when the diode is switched on, or the diode is switched on and the current flows when anode to cathode is greater than 0.7, charges up the capacitor, and the rest of the time the capacitor discharges through the resistor, which is the same situation as previously. There is no difference at all sort of analytically between this and the regular peak detector. So the triangular approximation to the black line will become important later. But this smoothing has caused our current shape, the wave shape of our current, to go from half the time it's more than zero and changing in size, and half the time it is zero. Now we've got quite a sharp spike between, well, I don't know, 2 milliseconds and about 6 milliseconds by the looks of things, and then another one between 22 and 26 or thereabouts. And all the energy is contained therein. So if we were going back to what happens if you run a motor off this and try and stall it, our torque situation has got even worse, because now your torque is in really confined regions and the vibration is going to be a lot worse. So actually we've smoothed out the voltage and we've made the situation for driving load more difficult, possibly. And this rapid change in current can cause some problems, because if you have a sudden DI by dt, what you end up with is lots and lots of high frequencies. Eventually you will come onto a kind of analysis that allows you to go between time and frequency domain, and when you do you'll find out that fast changes in voltage and current lead to high frequencies existing. And one of the problems is high frequencies like to travel, and if your circuit can look a bit like an antenna, your high frequencies leave your circuit and get into anything they can that surrounds them. And that sort of, or the analysis of those sort of problems is dealt with in EEE 6010, and broadly speaking that area is called electromagnetic interference. So the external supply, that's to say V in this graph, in this figure, sorry, is supplying most of its energy in that short region where there's a big current. The rest of the time, it's not doing much. And that's the cause of the impulsive mechanical loads. And these pulses are even worse than just that, because if you've got a big current flowing for a short time, in that short time you'll have a big I squared R loss. If you had a smaller current flowing for a longer time, you'd have a smaller I squared R loss, which would be preferable. So big impulsive currents, very, very bad. Luckily, transformers aren't perfect, as I previously described, and they have a bit of resistance along with them, because they are really long copper wires which are wound around magnetic material. And the long copper wire has a certain resistance per unit meter, per unit length. So if you've got 100 meters or 50 meters of wire, you might have a significant resistance sort of in the region of a couple of ohms. So we can say, well, what happens if the transformer's a bit more realistic? So black and blue, top graph, black and blue are a very, very, very good transformer, in quotes, and green and red are a more realistic transformer. And the top graph is voltage and the lower graph is current. And we can see that the more ideal transformer, which is the undesirable one, has big impulsive currents that last only a short time. A more realistic transformer has less impulsive currents, so not as high amplitude, but spread out over a longer proportion of the period of the waveform. Of course, ideally the green line and the black line, which are both output voltage, would be the same height, but they're not. So we lose a bit of voltage output at the expense of the transformer's inadequacies. On the other hand, those transformer inadequacies aid us in getting better current profiles in our power supply. The only other things to say is that for the green line and the black line, we can make the assumption for both that the waveform which represents the output voltage has a ripple, and that ripple is still triangular, and we'll use that later to make some calculations a lot simpler. The other thing to say is that if you buy a transformer, the manufacturer will not give you the information required to produce this sort of graph. You have to either make it up or work it out, and it's not trivial to do. So there will be no exam question that says, these are the imperfections, deal with it, because it's not the sort of thing that I'd want to ask. If you are buying a transformer, you'll find that there's something called regulation, which is not regulation in the sense that I will discuss it in this course. It is to do with how much variation there is in output voltages for certain input voltages. And generally speaking, the bigger the transformer, the better the regulation is. And if you were buying a sort of couple hundred VA transformer, you'd expect about 5%. If you want to know what that's all about, go and look it up on the internet, or in a book, even better. So lastly, the output voltage from a simple linear power supply, which is what we're discussing here, with capacitor smoothing, is not very well defined. And it will often be lower than what we calculate. And how much lower will be a function of how much load we put on the power supply, so how big its load resistance is. Nevertheless, the calculations are still valid, because there will either be a best or a worst estimate, depending on what we're calculating. So we said that we could smooth out the current, well, you could smooth the output voltage by adding the capacitor to make it into a proper peak detector. So how do you choose the size of that capacitor? Well, I've already said that we can assume most of the time that the ripple is triangular. So we can do a bit of maths on it. So between the two lines that represent the ends of T2, the capacitor is discharging, and across T1, the capacitor is charging up. We're also going to say that the transformer and the power source are ideal. That's to say, there are no extra impedances that we don't know about, the supplier can't tell us, and we have to do some calculations to find. We're not going to worry about any of that. The other thing we'll say is that the load that we put on this power supply will not change throughout the course of our calculation. So if it was a 1 ohm resistor at the start, it will be at the end as well. If it was 10 ohms at the start, so it would be at the end. And we'll say that discharging occurs across all of T2, that is accurate. The other thing we'll say is that it charges up, the capacitor charges up instantly. There is no period in time when the capacitor has to charge up. We'll say it happens immediately. Now, because this is a half-wave rectifier, we'll only get the start of we'll get current conduction in the diode at the beginning of every other half cycle. That's to say, only this half cycle is worth having. This one contributes nothing. So charging will happen around here, and then around there, and not this one, the next one over there. So if you need to know what the value for T is, the period of the waveform, it will be 1 over the supply frequency. Later we will see in other circuits that this value can change. So if the load is purely resistive, as I showed back here, we will find that we can say the charge is the capacitance times voltage, the current is the change in charge at time, which is also C dV by dt, so we can say that C is VR upon T. It's just two formulas and a bit of substitution. The best thing to do is prove it yourself in your own time. But we'll do an example shortly. So in this case we can say for the purely resistive load, the load current is √2 times Vs upon RL. The √2 turns up because we're saying it's sine waves everywhere, and the relationship between the peak of the sine wave and its RMS value is √2. Vs upon RL is Ohm's law. I is V upon R. So if we were to do an example, we could say, perhaps, a half-wave rectifier power supply is loaded by a power amplifier which is driving an AC machine. That's just hyperbole to set up the question. Doesn't tell you anything. The load can be modelled by a 5 ohm resistance. Find the ripple voltage if the smoothing capacitor bank has a total capacitance of 68,000 microfarads, or 68 millifarads, and the transformer's secondary voltage is 80 volts RMS. So we've dealt with the transformer because I told you what the secondary voltage is going to be, and you know what the load resistance is, and you know what the capacitance is, so the only thing left to do is a bit of maths. Best thing to do is draw a little diagram first. I haven't bothered here, but if you draw a little diagram, you'll have something to look at which instantly tells you the information. So first thing is find the peak load current. And we can use the formula from a couple of slides ago, which is √2 gives us the peak, Vs upon RL gives us the current. And we're assuming there is no voltage drop across the diode. So what I'm saying is, way back when we started on diodes, I said you can say it's either reverse bias, nothing happens, 0 volts or more, perfect conduction. And I said, well, hang on a minute, you really need 0.7 volts as well, because that's how much voltage you need to get conduction. So we started using a 0.7 volt voltage source. Well, compared to 80 volts, 0.7 isn't really worth worrying about. All it does is make your equations a bit longer, makes the chances of a mistake a bit greater, and we can just take it away without losing very much in terms of accuracy. If the whole thing was 5 volts, 0.7 volts would be quite significant, and we wouldn't be able to ignore it. So √2 times 80.5, 22.6 whatever. And we need to know how long the smoothing capacitor will be discharged for. So what we're saying is, in T1, the peak current will be 22 amps or thereabouts, and between the end of T1 and the end of T2, there will be some time which we will be discharging this capacitor for. And what we're going to say is that actually, the capacitor charges up instantly, and T2 is more or less the whole cycle. So we're going to say it's 20 milliseconds. That's somewhat inaccurate, but it makes everything quite a lot easier. So that being the case, we'll use the expression from this slide, which is derived from Q equals CV and I is dQ by dt, and then knowing that I is also C dV by dt, sub that all in and put in some numbers. Low current is C times VR upon T, and VR is IL T upon C. So put in all the numbers and we get out a voltage. A couple of problem sheets will make this very clear. And in a couple of weeks I'll give you a problem sheet which has got this sort of question on it. In many cases this is a bit of an overestimate for what the ripple will be. But since we want to minimise the ripple, knowing the worst possible value is much better than knowing some intermediate value and having to sit there going, well, it could be worse than this. We'll have to put in some fudge factor. This is as bad as it can get, and that's the best thing that we can know. So moving on from the half-wave rectifier, we have a full-wave rectifier, which is just the addition of another diode. And the reason that we want to add the other diode is because in the half-wave rectifier, we only take half the waveform, the positive half cycle, and the negative half cycle is just ignored, really, it's wasted. So this circuit will allow us to rectify both the positive and the negative half cycle. And that's more or less what I've said on the slide. So the output waveform for this circuit with no capacitive smoothing is now almost the same as the half-wave rectifier, with the exception that every other half cycle is just flipped up. So you could say that this is also an absolute value circuit, because if I said you've got sine omega t times A, where A is the amplitude, what's the absolute value of it? You take every other, the lower bits, and just flip them up, which is what this circuit does. And there are methods of making a better absolute value circuit using a circuit very similar to this one, and they will be covered at some later time in some other course. For the moment though, we're worried about power supplies. So could it be that we can make it even better? We'd like simultaneous outputs of positive and negative, because we ought to be able to rectify full wave the upper and the lower halves, the first and second half cycles, then get an output voltage with positive, and we ought to be able to do the same and get an output voltage with negative as well, by judiciously placing capacitors that will charge up. We can. So now we've got 4 half-wave rectifiers. Previously we had 2 half-wave rectifiers, and before that we just had the 1. So the current in I1 always flows, except for a very, very small period of time where the input voltage crosses 0, and then the current's 0. But for the rest of the time there are no long gaps. And the same is true of IR2. And this is called a full-wave bridge. And you won't often see it drawn out like this. It's just that it makes clear that it's still a peak detector, peak detector essentially, minus the capacitor. Usually we draw it like that, and if you look in a textbook, this is how you'll see it drawn. It is the same as the previous slide. All I've done is rearrange it. It's like turning a donut into a teapot or something, except you can't, because the teapot's got 2 holes and the donut's only got 1. And if you're into mathematics, the area of mathematics for rearranging stuff like this is called topology. It's great fun. You get sort of questions like, there are 7 bridges in Vienna and you want to cross them all once exactly. Do it, and you can spend 300 years trying to get an answer. So this is just a rearrangement of the prior circuit. They are in fact identical electrically. And we can get two outputs. We can decide what we want to call our reference. We can say, well, C will be our reference, and D will be bigger than C, and E will be less than C, if we like. And if we did that, that would be really useful, because we could say run an operational amplifier, for example, because that is a component which needs positive voltage and negative DC voltage to run. Not just +5 and 0, it requires +5, -5 and 0, or ± 15, whatever. But if we wished, we could say that E is going to be our reference, and that C will be some value greater than E, and that D will be the same amount greater than C. So we could have 0, +15, +30. And there's nothing to stop us doing that. It just depends what we want to call our reference. In a real situation, we'd often put the earth from the mains onto whichever one we wanted to call our reference, and all the others would just align themselves accordingly. So you could put the earth on C and use D as plus and E as minus, or you could put the earth on E and use C and D as both positive, where E to C is plus a certain amount and E to D is twice that. So we can arrange our references however we choose. And similarly, in the half-wave circuit, as long as you've got a transformer in there, you could, if you wanted, make the upper point of R1, where I've got the current flowing, you could make that 0, and you'd have minus a certain output voltage on the bottom of R1. It's entirely up to you, depends how you want to wire it up. So a positive and negative output with respect to node C, which was the first thing that I said, used extensively in analog systems where you've got bipolar signals. That's signals which go above and below 0, and it's usually called a center 0 power supply, especially in American textbooks. The other obvious situation is a single output at node D with respect to E, and this is a low-cost version. So if you want a car battery charge or something, you need to shave 10 pence off because you're going to make 100,000 of them, and you need to sell at a certain price point to make a profit of a certain amount. You might have to drop a component or use a cheaper one, or possibly take away a certain output. So that would be the situation where you don't worry about C, and you've got one resistor from D to E, and you call E the reference. So the smoothing of the full wave rectifier. So everything except the very first one is full wave of some kind or another. The only difference really, or the main difference, is that the capacitors are charged up once per half cycle, not once per full cycle. So to get a certain ripple specification, you can make your capacitor half as large, which is good because that will make it a lot cheaper, probably more than half cheaper. And these capacitors will be charged up twice per input cycle, because we'll rectify the input to get the blue line, and the capacitor will charge up first on between 0 and 3 or 4 milliseconds, and then again between 10 and 13 milliseconds or so, and again between 20 and 23, and so on. So if you look at the input cycle, which is 0 to 20 milliseconds, you get charging around 3 or 4 milliseconds, and again around 13, 14 milliseconds. That's twice in one input cycle, which is different to the, this one will do, different to the full wave rectifier, sorry, half wave rectifier, where it's once only per input cycle. We can see it's charged up between 2 and 6 milliseconds, and then again between 22 and 26 or thereabouts. So that's once per input cycle. That's really, mathematically speaking, the only difference. Electrically they work well, broadly they work the same, except one is an extension of the other. But when you come to do the calculations, the only thing you have to remember that's different is capacitors are refreshed at twice the input frequency in full wave, and half the input and at the input frequency in half wave. In all other respects, behaviour is the same. So as I've just said, because of this, prior equations can be used to choose a capacitor to meet the ripple voltage requirements, or to estimate the ripple given a certain set of values. So one exam question might go along the lines of, here are some values, what's the ripple? Another might go, here's a particular power supply circuit, any one of the three. I need this much ripple, this is my load, how big should the capacitor be? That's the sort of thing you'll find on the problem sheet, and that's the sort of thing that's going to end up in the exam. So, full wave, 100 Hz in Britain, 120 Hz in the States. Half wave, 50 Hz in Britain, 60 Hz in the States. And that's broadly it. So we introduced some linear power supplies, and we briefly discussed some differences between single phase and three phase. And then I talked about the half wave rectifier for quite a long time. And we said that it's basically a peak detector in disguise. And then I gave you a simple model to determine what the size of the capacitor should be, where we assume that the ripple is triangular. And then we say, well, there's this much charge going in, I, C, dV by dt, throw it all together, you can come out with ripple voltage. And then we said that the full wave and the bridge are both extensions of the half wave by adding peak detectors in judicious sort of arrangements. And the last thing I said that's important is that in the full wave circuit, the capacitors are refreshed at twice the input line frequency, and in half wave circuit they're refreshed at the input line frequency. And the other thing I said that's worth remembering is that the output voltage that you get depends what you call your reference. And in a real situation, that's where you put your earth. That's it. Quick, to St George's.